Hello, cowboys and cowgirls. Happy New Year. Welcome back. We are starting this second semester with Unit 5, and our 5.1 lesson is going to be on our cubic functions, but we're also going to introduce some characteristics of polynomials because this whole Unit 5, is really majority covering polynomials. But before we really dive into polynomials, we need to understand what a cubic function looks like and how to graph it. So what we're going to do first is we're going to go over some polynomial characteristics, and then we'll get into our cubic functions. So a polynomial is a algebraic expression. And if you look up here on the right hand side in this box, it tells you if it has one term, it's called a monomial, two terms, a binomial, three terms, a trinomial. So poly just means many. Just like a polygon has many sides, a polynomial has many terms. So it could have one, it could have two, it could have three, it could have seven, it could have five, it could have however many that you want it to. That is a polynomial. You are already familiar with some of these polynomials. If your polynomial has a degree of 1, and the degree is indicated by the exponent on that variable. So let's just say I have x to the first power. That would be a first degree, which we know is just a linear function. If it's a second degree, then that means our degree is 2, so that would be something like x squared. Well, then we know that that is a quadratic. And then today, what we're going to cover is that degree of 3, and then that is our cubic. And then anything over that, you could call it like a fourth degree is called a quartic, but really we just say it's a polynomial with 7 terms, or it's a polynomial with 5 terms, or whatever. These are just the most common. When we're dealing with polynomials, all of our exponents are going to be those whole numbers. They're not going to have fractions. They're not going to have variables as exponents. It's going to be either x to the first, second, third, fourth, fifth, sixth, so on and so forth. All whole numbers for exponents. There will also be no variables in the denominator. So if you come across a polynomial that is a fraction, so you have a numerator and then a denominator, in your denominator there will be no variables. And if there are, we might have to move it, or maybe we just can't do that specific problem. There also will be no variables underneath a radical, a square root sign. We've been dealing with radicals before break, and we'll deal with them again, but there's going to be no variables underneath a radical for a polynomial. And then lastly, which is most important when we're graphing, is that a polynomial graph is continuous. There's no sharp turns, there's no holes in it. It's very smooth and continuous. It kind of reminds you of like rolling hills, or like an easygoing roller coaster, nothing with sharp turns and no holes. And so, like I said, obviously that's going to be very helpful when we go to start graphing, which will be next lesson. Another couple words that we need to be familiar with is the degree, the leading coefficient, and then what is standard form of a polynomial. Well, the degree is going to be the highest exponent you see when it's written in that standard form. And so standard form of a polynomial is whenever your highest exponent is written first and then going in descending order after that. So let's say we have an x squared term, an x cubed term, and then an x term. Well, that would not be in standard form because the cubic is not first. We want the highest exponent first and then going down in sequential order, just backwards. And then, of course, our leading coefficient is the coefficient of the highest power term. So the highest term, or the term with the highest exponent, that degree. Also, something to note, you can easily pick out the degree of a polynomial because it is the highest exponent that you see when it's written in standard form. That number will also give you something significant when it comes to graphing, and that is that there will be at most whatever number that is minus 1 turns on the graph. So let's say the degree of the polynomial is 5, then that means the graph will have at most 4 turns, 5 minus 1. Let's say the degree is 6, then it could have at most 5 turns. That doesn't mean that it has to have all 5, but that's the highest number of turns I could have. Turn meaning a change in direction. So just showing you an example, this is a turn, that's another turn, that's a turn. 1, 2, 3 turns. Change in direction is a turn. All right, so like I said, that's just a really quick introduction. We're going to get into more polynomials in the next lesson. But before we move on to cubics, let's just kind of put those vocabulary terms to test real quick. So example 1 says, determine whether each of these is a polynomial. If it is, find the degree. And if the polynomial is not written in standard form, go ahead and rewrite it so that it is in standard form. And then we want to classify the polynomial by the number of turns and degree. So first things first, is this a polynomial? Well, I see that my exponents are whole numbers. I don't see any variables in the denominator. I don't see any variables underneath the radical. So yes, this is a polynomial. Second thing I need to do is find the degree of that polynomial. The degree said it's the highest exponent when written in standard form. And standard form is putting that highest exponent first. So the highest exponent here is not written first. So let's rewrite this. The term with the highest exponent is the 7x cubed. And that's a positive 7x cubed. The next term in decreasing order would be that squared term, which is a negative 2x squared, this one right here. And then the last term would obviously be that negative 3. There is no x term in this polynomial, but that's okay. We're still in decreasing order with the highest exponent first. And so now that we see that highest exponent first, this means that our degree of the polynomial would be, good job, 3. And so because the degree is 3, that means the number of turns, it would be at most 2, because it's always the degree minus 1. All right, moving on to the second one. First thing, is this the polynomial? And we are going to say no. The reason why it's not a polynomial is because of the exponent of x right there. That is a variable as an exponent. That means that it is not a polynomial because it says all exponents are whole numbers. And we don't know what x is representing. And in fact, it changes. X is, could be a million different things. So we don't know what that is. We need to see those whole numbers for it to be a polynomial. So that's not a polynomial, so I can't answer any of the other questions. And then lastly, I want to know if this is a polynomial. And it actually is. We have to be very, very careful here. We do see a radical, but the variable is not underneath the radical. Just the 5 is underneath the radical. So the square root of 5 is just some coefficient. That's okay. The x is not underneath it. The exponent is a whole number, so this is good to go. So yes, it is a polynomial. Is it written in standard form? Is the highest exponent first? Yes, it is. There's only 2 terms. It's a binomial. And our highest degree is 2, which means it's going to have at most 1 turn. All right, so moving forward to cubic. So remember, cubic is my third degree. First degree is linear, second degree is quadratic, third degree is cubic. So we want to start off with our parent function, something that has not been transformed. So no stretches or compressions or flips or slides or anything like that. Just the basic cubic parent function, and that's just going to be x to the third power. As always, I like to create a table of values, plot that, and then based on the table and the graph, answer the characteristics, with domain, range, increasing, decreasing, etc. Because I like to get an idea of the graph on both the left and the right side of 0, the negative and the positive, let's choose -2, -1, 0, 1, and 2. So if I plug in -2 inside that variable of x, then that means I have a -2 cubed, which means I'm multiplying -2 times itself 3 times. Well, -2 times -2 is a positive 4, times another -2 is going to be a -8. If I change that value of x to -1, then negative 1 times negative 1 times negative 1 is negative 1. If I plug in 0, that's going to give me 0. If I plug in 1, that's going to give me 1. If I plug in positive 2, that's going to give me a positive 8. So I'm going to go ahead and now plot these 5 ordered pairs. Negative 2, negative 8. Oh, let me make this a little bit bigger. Negative 2, negative 8. Negative 1, negative 1. 0, 0. 1, 1. And 2, 8. And when I go to connect those dots, I get the parent cubic function. It's kind of like this snaky, squiggly, not really squiggly because it doesn't really go up and down, but just this continuous curve. Notice the word I just used, continuous. There are no sharp turns or holes. So is this a polynomial? Yes, absolutely. It has a whole number exponent. There's no variables in the denominator. There's no variables underneath a radical. The graph is continuous with no sharp turns or holes. Okay, so very smooth and gradual kind of continuous shape for the cubic parent function. So domain. Remember, domain are the x values from left to right. This is going from negative infinity all the way to positive infinity. Range, again, all the way from negative infinity to positive infinity. Increasing. Where is this graph going up from left to right? The whole entire thing is increasing. When I connected those dots, notice my pen never really changed directions. Not even right here in the center part. I just did a little swoop-de-swoop. I didn't change directions, right? So this is increasing the entire way, which means it's not decreasing anywhere. Where's the graph positive? So remember, positive means where is it above the x-axis? Where are the y values greater than 0? Well, that's starting at 0 and going all the way to infinity. Oh my God, excuse me, I just burped. Where's the graph negative? Where is it below the x-axis? From negative infinity all the way up to that 0. Does this graph have symmetry? Well, when we first look at it, we're thinking, no, it's not symmetric about the y-axis. It's not symmetric about the x-axis. It's not symmetric about the line y equals x. However, this does have some symmetry, and we call it origin symmetry. And origin symmetry means that if I were to rotate this 180 degrees, or if I were to flip over the x and the y-axis, then I would get the exact same result from the original. We're going to talk about this later on, but this also means, because it has origin symmetry, that it is an odd function. Okay, we're going to talk about that later on, but I just want to kind of put it in your ear now. The next characteristic is extrema. If you remember, extrema means your maximums and your minimums. Well, because this graph doesn't have any turns, it doesn't have any change in direction, there is no max or min. There's no highest of the high and lowest of the low, because it goes on forever. What we need to talk about here, though, is this point in the middle, where it does kind of do that little like change, but it's not a change in direction. It just kind of glides over. We call that the point of inflection. It's like a vertex. It's like what you would call the vertex. Remember the vertex of a parabola? Well, we can't call this a vertex because it's not at an extrema point. It's not at a maximum or a minimum. So we call it the point of inflection. And you may have heard the word inflection before. Sometimes you can think of that as like a change in your voice and pitch, adding inflection to make a statement turn into a question or something like that. So for our parent function, the point of inflection is that origin. It is 0, 0. And if you can think about it, it's also kind of changing, like from positives to negatives, looking at that chart. And then lastly, we have that in behavior. So remember, in behavior, as x approaches negative infinity, your y values are also approaching negative infinity. And as x approaches positive infinity, those y values are also approaching positive infinity. So here's your parent function, and like always, we're going to transform it now. These transformations have not changed, so hopefully you know them by heart by now, and you can just fill in this table with no help or no kind of hiccups. So when we see something inside of the parentheses, remember that's always horizontal and it's opposite of what we think. So this is actually going right, left, and then this will be your horizontal stretch or compression. So this will be the horizontal stretch. And then this one will be the horizontal compression. And then horizontally, we are flipping over the y-axis. So x minus some number cubed, x plus some number cubed, some number times x cubed, or the opposite of x cubed. Everything on the outside of the parentheses we know is vertical. So plus, I'm going up, negative, I'm going down. A number in front means I'm either getting smaller or bigger. And then a vertical flip would be reflecting over the x-axis. So x cubed plus a number, x cubed minus a number, something times x cubed, and the opposite of x cubed. And then again, what I call that skeleton down here, kind of showing everything put together. Please, 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 please be careful with that b value. We always, always, always want to factor it out. Okay, so if we see something like, let's just say it's 1/2 x minus 4 cubed. We need to factor out that 1/2, leaving me with x minus, what would that be, 8 cubed. Okay, please, please, please be careful with that. All right, so with that reminder of our transformations, now we get to the actual problems that have been transformed, our cubic functions that have been transformed. So we're going to list out the transformations, identify the point of inflection, maybe list out domain, range, end behavior, increasing, decreasing, whatever characteristic they ask, and then of course sketch that graph as well. I want to go back up here really quickly. So with that parent function, if you're going to graph like I do, which is according to a pattern, remember with the quadratic pattern, we went from the vertex, right 1 up 1, right 2 up 4, right 3 up 9, right 4 up 16, because we were squaring the number. Well, now we're cubing that number. So when we go right 1, we will still go up 1, right 1 up 1, but when we go right 2, we're going to be going up 8 because 2 cubed is 8. And if we went right 3, 3 times 3 times 3 is 27. And if we went up 4, or right 4, then we would actually be going up 64 units, which obviously won't be fitting on any of these graphs that we do. But that is the pattern of graphing a cubic function. It gets pretty steep really quick because you're not squaring a number, you're cubing a number. And so they can get really high. So you are very safe, knowing these. So if from the point of inflection, which is here, 0, 0, if it hasn't been transformed, I would go right 1 up 1, right 2 up 8, left 1 down 1, left 2 down 8. That is going to be my pattern of graphing. All right. So down here, list out the transformations. So what I see here is that we're going to the right 3 and down 4, which means that is our point of inflection. Very, very, very similar to that vertex. We just can't call it the same thing. All right. So let me go ahead and plot that point. 3, -4 is here. Because there has been no vertical stretch or compression and no horizontal stretch or compression, my pattern of graphing is going to be the exact same as the parent function. So I'm going to go right 1 up 1, right 2 up 8. 1, 2, 3, 4, 5, 6, 7, 8. From that point of inflection, left 1 down 1, From the point of inflection, left 2, down 8, which is obviously going to be off the graph, but let me just estimate 1, 2, 3, 4, 5, 6, 7, 8, somewhere about right there. And then I'm going to connect those dots with a smooth and continuous line. And there we have it. Because there has been no flips, domain is still negative infinity to positive infinity. Range is still negative infinity to positive infinity. Is this graph increasing or decreasing? It's increasing the entire time. Let's try it again. So here we do have a vertical compression. We're going to the left 2 and down 1. So point of inflection is negative 2, negative 1. So I'll go ahead and plot that. Negative 2, negative 1 is right here. There has been a vertical compression. So instead of going right 1, up 1, I only want to go right 1 and up half of that. Well, half of 1 is half. From the point of inflection, instead of going right 2, up 8, I want to go half of that. So I'm going to go right 2, up 4. From that point of inflection, I'm going to go left 1, down a half, because it was normally left 1, down 1. And then I'll also go left 2, down 4. Again, a smooth, continuous line. See, I didn't even hit all the points, and that's okay. And there's my cubic function that has been vertically compressed, shifted left and shifted down. Notice my domain is still negative infinity, positive infinity, and my range is still negative infinity, positive infinity. Think about if that's ever going to change. And if you want to pause the video and kind of think about some different scenarios. In behavior here, as x approaches positive infinity, y is also approaching positive. As x approaches negative, y is also approaching negative. All right, let's try it again. Negative 2 x cubed minus 1. Negative in front means I'm reflecting over that x-axis. Let me change my color actually. Okay. So I'm reflecting over the x-axis. There's a 2 in front, so that means it's a vertical stretch. And then there's a negative 1 at the end. There are no parentheses here, so nothing is happening horizontally. That negative 1 at the end means I'm going down 1. So that means my point of inflection is at 0, negative 1, which is right here. If you want to plot write out the pattern of graphing from the point of inflection, right 1, up 1, right 2, up 8, left 1, down 1, left 2, down 8. And then alter it as needed. So I'm going to change colors real quick and say, hey, if I've reflected over the x-axis, everything that was going up is now going to go down. And I'm vertically stretching. So everything is getting multiplied by that 2. So this positive 1 is now going to be a negative 2. This positive 8 is now going to be a negative 16. Negative 1 is now going to be a positive 2. Negative 8 is now going to be a positive 16. So if I go and graph that, right 1 down 2, right 2 down 16 won't fit. So from my point of inflection, left 1 up 2, left 2 up 16, it still won't fit, but you know it's going to be somewhere up here, maybe even a little bit higher than that. And so you really now see that vertical stretch take place, and you also see that reflection over the x-axis. So instead of going kind of up and to the right, now it's going down and to the right, which makes sense because it's been reflected. And so then that answers our question, is this graph increasing or decreasing? Well, because it's been reflected, it's now going down from left to right. So it is decreasing the whole time. Okay. Now over here on the right-hand side, we do see some parentheses and we do see a negative inside. But remember, anytime you have parentheses, I need you to factor out whatever's in front. So let me go over here and rewrite this as negative x minus 3 cubed plus 1 to see how it changed the direction of the shift. Instead of shifting left, we're actually shifting right. So because there's a negative inside the parentheses, that's a reflection over the y-axis. We factored it out, so we got a shift to the right 3, and then that plus 1 at the end didn't change, so that's still going up 1, which means our point of inflection is at 3, 1. The only thing that's changing my pattern of graphing is the reflection over the y-axis. So again, instead of going right and up, now I'm going to go left and up. Instead of going left and down, I'll go right and down. So instead of going right one up one, I'm going to go right one down one. Oh, I'm sorry. No. Instead of going right one up one, I'm going to go left one up one. And then instead of going right 2 up 8, I'll go left 2 up 8. 1, so that was at 1, so it'd be here. Instead of going left 1 down 1, I'll go right 1 down 1. And then instead of going left 2 down 8, I'll go right 2 down 8. And so then I should have zoomed in. Then I see my cubic function. No stretch, no compressed, but it has been shifted and flipped. In behavior here, as x approaches negative infinity, y approaches positive. As x approaches positive, y approaches negative. Getting close. All right. Again, here we see one where we see those parentheses and we see something in front of the x. We have to factor this out. So again, I'm going to rewrite. I'll come over here and say this is really 1/3 times x minus 3 cubed. Because if I distribute that 1/3 times 3 is going to give me that 1. So that 1/3 is representing a horizontal stretch. And then the minus 3 on the inside is signifying a shift to the right 3 units. So that's where my point of inflection is at 3, 0. 3, 0 is here. Horizontal stretch of 1/3. So everything's being divided by 1/3, which means it's being multiplied by 3. So instead of going right 1, up 1, right 2, up 8, horizontally, so that's the x, the left and the right, this is going to be multiplied by 3. This is going to be multiplied by 3. So instead of going right 1, up 1, I'll go to the right 3, up 1. And instead of going right 2 up 8, I'll go right 6 up 8 all the way up here. And then the same thing on the left-hand side. Left 3 down 1, left 6. 1, 2, 3, down 8. There we go. A smooth, continuous, my hand's a little shaky, but that's okay. Smooth, continuous line to connect those dots. And then is it increasing or decreasing? Increasing the whole time. Domain, negative infinity, positive infinity, range, negative infinity, positive infinity. If you haven't noticed, domain and range will never change. Also, increasing and decreasing will always be negative infinity, positive infinity. It just depends. Some are increasing, some are decreasing, depending on the reflections. And then the last one like this. There's nothing in front of the x inside the parentheses, so we don't have to change anything. That 3 out front is telling me that it's a vertical stretch. Inside the parentheses, I'm going left 4 and then down 3. So point of inflection is -4, -3. So I'll go ahead and plot that. -4, -3 is here. A vertical stretch of 3 means instead of going right 1, up 1, right 2, up 8, I'm going to be multiplying this by 3. Obviously, I cannot go that high up on my graph, but I can go right 1, up 3, and left 1 down 3. And then I know my right 2, up 24 is way up at the tippy top. So I know this is going to be extra skinny. And that's okay. In behavior, as x approaches infinity, y approaches infinity. As x approaches negative infinity, y is also approaching negative infinity. That would be increasing from negative infinity to positive infinity as well. And then the last two examples are kind of the opposite of what we just did. I'm going to give you a graph and you need to figure out what transformations have been applied. To help you do that, I put a little stipulation on the first 2 graphs and the last 2 graphs. The first 2 graphs, I'm telling you, they have to have a B value of 1. And remember that B value is that horizontal stretch or compression. So for the first 2 graphs, there is no horizontal stretch or compression. So it's only vertical, if at all. So what I'm going to do first here is I'm going to try to identify my point of inflection and some other really good points on it, and then see if it follows the pattern 1 1 2 8, etc. My point of inflection is right here, and then I see two really good points here and here. Well, this tells me from the point of inflection, I went right one, down one, and I went left one, up one. Well, the pattern of graphing from the point of inflection is normally right one, up one, left one, down one. Well, we're really close to that. We went right one, down one, and left one, up one. So these directions have changed. So that means that I have reflected over the x-axis. So to write that, I need to start with a negative in front. I also noticed that that point of inflection, let me erase this mumbo jumbo. This point of inflection is not at 0, 0. So it's been shifted over. It's at 2, 4. So that means it went right 2 and up 4. And now you should be able to kind of work backwards. If you looked at that equation, you would say, okay, this has been reflected over the x-axis. It's been shifted right 2, up 4, no stretches or compressions. This is the graph that you would have plotted. All right, let's try it again. This time, my point of inflection is right here. And I see a really good point here and here. So, and you could also kind of use this as a guide as well. And I'll talk about why in just a second. Let's look at our point of inflection first. Our point of inflection went left 3, down 1. This is -3, -1. So I already know how to write that. That's going to be x plus 3 cubed and then a -1. What I don't know is what number goes here. Because remember, b is still 1. So there's only an a value that's applied, if at all. Well, did this graph go right 1, up 1, right 2, up 8? No. It looks like it went right 1, up a half, and then it went right 2, up 4. Well, that makes me happy because what's half of 1? Half. And what's half of 8? 4. So this means that this graph has been vertically compressed by a half. Right 1, up a half, right 2, up 4, left 1, down a half, left 2, down 4. It all matches out. The directions are good, the numbers are good, so this has to be our equation. Okay, the last two examples kind of switch it. Now they're saying assuming that this has an a value of 1. So that means if it's been stretched or compressed at all or reflected, it would have to be horizontally. Okay, again, I still want to locate that point of inflection first and some other good points on the graph so I can figure out how the pattern has been altered. This first one might be a little challenging, but our point of inflection is actually right here at 2, -2. So again, you could already start by saying, I know it went 2 to the right, and then I know it went down 2. The reason why I'm not going to go ahead and do this is because there could be a b value. Then I would want to do this. And it looks to me like it's definitely been stretched horizontally. Don't you agree? I hope so. I'm going to put this really good point, right here and this really good point right here. And what I'm going to do is I'm just going to think to myself, because it's been horizontally stretched, I know that, I can tell that. Let's just count. 1, 2, 3, 4, up 1. It normally goes right 1, up 1, but now it went right 4, up 1. Well, let's see if it goes left 4, down 1. 1, 2, 3, 4, down 1. I can't see anything past that, so I know that it's been horizontally stretched by a factor of 4, which means I need to see a 1/4 right here. And that is our function. Direction is fine. It's just been horizontally stretched. If I just put a 4 there, that would have meant it would have been horizontally compressed. So it would have been really, really tiny. Okay, which is not the case. So it needs to be a number between 0 and 1, which is 1/4. And then our last one looks like, remember, if we're still thinking about horizontal, it looks to me like this would be horizontally compressed. So that means I want to see a number bigger than 1 there for that b value. Here's our point of inflection. I'm locating this point here and this point here because really there's no good visible point. I don't know if it's hitting that point right there or not. I don't want to estimate that. But what I can do is I can just say, hey, I know it's been compressed. Looks like it went right half, down 1, left half, up 1. So not only has it been compressed, but the direction has also changed. So that means I need to see a negative. And then because it's going right a half, that means there's a 2 there. 2. And then where's the point of inflection? It went left 3. Not up or down any, so just left 3. And there it is. Ta-da! Oh, wait. Technically, actually, I'm sorry. This, because our a value needs to be 1, and I just had it as a -1, it needs to be a -2, and then it would have to be x minus 3 cubed. Because I know it's supposed to be x plus 3 because we went to the left, but remember, if there's a negative here and I would distribute it, that would be a -2x plus, 6. So it's all good in the hood. Wait, no. Oh, no, I'm wrong. Just ignore me real quick. Hold on. Okay, let's try this one more time. 3rd time's a charm, right? Okay, I was correct that the negative needs to be on the inside because it says assume that the a value is 1. Not a -1, but a +1. So now our a value is +1. -2 goes in the inside. This is still going to be x minus 3 cubed. This is what we want. We want it in this format so I know exactly what direction it's going. This would also be correct, but I don't want you to take that step because I always force you to go this way. So why go that way? Does that make sense? I hope so. So this is your final answer, even though this is technically correct as well. But I'm going to erase that because I don't even want you to think about that. All right, and that, my dear friends, is our cubic function and an introduction to polynomials, which we're going to get into more depth in 5.2. Adios.